Visible, sir.
Visible. Okay. So we were talking about the far flow diagrams and the equation to compute different losses and also input power and output power. I think you would have noted the equation yesterday. So today we will see one example problem to compute, because you can expect this kind of problem in exam.
Yeah, good evening, sir.
Good evening. A typical problem, what we saw yesterday, power flow diagram, how to compute losses and final power output, convert into mechanical power, we call a P output. From the power flow diagram, we can compute. For example, a problem, a 460 volt, 25 HP, 60 Hz, because this problem actually taken from a book, American book, so automatically will be 60 Hz in the power supply. And it is a 4-pole motor. That means P equal to 4. And it has following motor parameters. One is R1, that is stator resistance, equal to 0.641 ohms, and R2, which is nothing but rotor resistance. We are talking in terms of equivalent circuit, correct? So 0.0332 ohms, and X1 equal to 1.106 ohms. Please note that X1 is called as reactance. It is called sometimes colloquially they call it AC resistance. XL, you know that being inductive, this one XL equal to 2 pi FL. F is the frequency of the input. Here in this case 60 Hertz. L is the inductance value of the coil, stator coil. Then if you multiply this inductance value, they are not given. Instead of they directly they given XL itself. Okay. So similarly, X2 equal to 0.464 ohms. This is the rotor reactance. And XM, magnetizing reactance, already we saw equivalent circuit, we saw magnetizing reaction is 26.3 ohms. These are the parameters given. Then additionally, what they are given is other losses, total rotational losses they call. Rotational losses are 1100 watts they are given, and they say that these losses are constant losses. It is not going to vary depending upon motor speed or any other parameter variation. These are constant losses. And also they say the core loss. We saw that TCL, core loss, correct? Core loss is a lumped parameter. Is a lumped into a single loss. Into a single rotational loss. Okay. Then what they told is, because we know that in induction motor we need to know the slip also. Slip is very important parameter. The rotor slip, which we call as small s, equal to 2.2%. That means it is 0.022, correct? It varies from 0 to 1. Absolute value is 0.022. Otherwise, percentage multiplied by 100, given 2.2% they are given. At the motor rated voltage, they say 460 volts at rated voltage. and frequency. Frequency already given 60 hertz. What they are asking is to compute this speed. A, B is stator current. Stator current, we know it is nothing but I1. Then power factor. Then they wanted to find out P, power converted. Power, the electric generator converted into the magnetizing, correct? Which is converted into magnetizing power, which will be transferred to the rotor, correct? First magnetic power, and also final P out, that is mechanical power. Then they are also asking you to compute induced torque. T-I-N-D means tau. Sorry, it is called tau. It is nothing but induced torque. And the load torque. Load torque, they have mentioned tau L. Lastly, they wanted to find out the efficiency of this motor. Sorry. Efficiency of motor. 7 parameters they ask you to compute using the data available in the problem statement. Okay. Let us do one by one using the equation what we learned yesterday. Okay, this one. First thing is they ask you to find out speed, which is nothing but ns. Ns is nothing but synchronous speed. Synchronous speed we need to find out. We know that ns equal to 120 f divided by p, and we know that it is 120 is a constant. For this problem, f is given as 60 hertz because being American the power supply. And they say it is a 4-pole rotor, correct? So the RPM is going to be 1800 RPM, correct? This is NS. This is the rotating magnetic field speed, not the rotor speed. Then we can find out NR. Sometimes it also called as NM. M is motor or rotor speed. This is shaft speed is nothing but 1 minus S into NS. We know that 1, they said 2.2, that means percentage, it is going to be 0.022 into NS. Already we know that 1800 RPM, that is synchronous speed. So if we compute, the NR will become 1760 RPM. NR we know. Now we have NS also. We have computed 2 parameters. Okay. So next, what is asked, this is the second part is B, to find the stator current. We know stator current is given as I1. We need to find out. Correct. So to find this one, first thing is they have not given the equivalent impedance. What they have given is X1, R1. Correct. They have given X1, R1 and R2, X2. Okay. So first thing is we need to find out equivalent impedance to find this I1. So we compute Z2. Z2 is nothing but R2 divided by S plus JX2. And the values of R2 is given, X2 is given. So we can substitute that. It is going to be 0.332. We know the S equal to 0.022, 2.2% will be converted into this one. Plus J, X2 already given 0.464. So many ohms. Now this can be reduced to, so Z2 can be computed. Z2 is going to be 15.09 plus J 0.464. 0.64 can be, that is in the complex form. In polar form, you can write 15.10 and with the angle of, phase angle of 1.76 degree, so many ohms. Right? This is the value you obtain Z2 equal to. Now, this is called Z2. What is the Z2? This is called a referred rotor resistance. What we referred with respect to stator. The equivalent circuit we are talking with respect to input voltage, giving this the stator voltage V1, because there's a current flowing through that. That current goes into the rotor coil. Some part of the current is used for magnetizing. Correct? So IM, remaining part goes through the rotor through a magnetic field generated as a transformer. Correct? The rotor coil and the stator coil, if you remember, I said it is like a transformer. The power is transferred magnetic coupling. That is the current supply from the stator is supplied to the rotor as a magnetic field. It induces a magnetic field that will be cut by the rotor. There's a voltage induced and the rotor coils are short circuited. So automatic current flows. That is what we call as rotor current. Rotor current is nothing but I2. I2 is the part of the current into the rotor. That already we saw equal. So I am not going to draw. Once again, we don't have time. So that means Z2 is called as referred rotor impedance. What referred with respect to stator coil, that is called equivalent. Actually, basically two, primary, secondary. Then I said equivalent circuit is the with reference to rotor side. So for that only the equation was written. Correct? This is Z2 equal to R2 divided by S into JX. Nothing but rotor impedance. Impedance means resistance plus the reactance. Together they are called as impedance. So the values were given, from that we computed rotor side. But we need to find out I1, we need to find a net impedance. Net impedance consists of the magnetization impedance plus rotor impedance. Together it forms the net impedance. We say that ZF equal to 1 divided by 1 by JXM. XM is called magnetic reactance of magnetizing impedance part of this one, plus 1 by Z2. This is the referred rotor impedance. So we know the values, so we can substitute 1 divided by J minus J, because being a complex quantity, equal to 38 plus 0.0662 with an angle 1.76. This can be reduced to 1 divided by 0.0773 minus 31.1. Correct? So this can be finally written in terms of polar form 12.94 and angle, this one so many ohms. This is the ZF. Okay. So once we know the ZF, then we can find out total impedance to compute the I1. Z total is nothing but Z stator winding. We are given Z stator and LD available plus ZF what we have computed here. This value. Both are in series, correct? Because this and this are in series. If you substitute this, what we can write is 64.641 plus J 1.106 plus 12.94 angle 31.1 degree. Okay. Please know that this is in polar form, this is in complex form. You can come polar to complex, complex to polar, you have to convert. Okay. That step you have to do. And if you do that, finally what you will get is complex quantity Z total in terms of complex quantity. this part can be converted into complex quantity, and the real part will be added, complex part will be added. Finally, you will get 11.72 plus J 7.79. You can use calculator in the exam allowed, scientific calculator, where complex quantity can be converted to polar, polar can be converted to complex quantity, because two different format you cannot do. First thing is you have to convert one form to another. From that automatically, from here, the final answer shown is a complex quantity. This can be from polar, it can convert to complex quantity. Then real part can be added, imaginary part can be added. From that automatically you can find out the final Z total. Okay, now that we have the Z total, now we'll go to compute the I1, correct? The stator current. I1 we need to compute. We know that I1 equal to V divided by Z total. Okay, in fact, we'll put phase voltage V5, and already V5 is what here is given is line voltage, correct? 460 volt line voltage is given, correct? So this can be converted to 5, means it will become 266, and angle equals 0 degree divided by 14.07. Z total already computed, divided by 36.6 degree. So, okay. I1, sorry, this is called I1. I1 is going to be 1888 with an angle minus 33.6, because the denominator go to this one, the plus will become minus, and if you divide 267 to this one, you are going to 18.